Today, we want to grab a new shape and start thinking about this shape in terms of integrals, double integrals, and triple integrals. The big goal that we're trying to accomplish is learning how to describe regions and solids in ways that integrals will understand. Because the integral works by taking an expression and evaluating it at a bunch of points. We have to make sure that we can tell the integral what points we want to plug in. With single integrals, it's all very simple. We're just plugging in some interval on the x-axis. Nothing interesting can happen there. There's a start, there's an end. We want all this stuff in the middle. It's weird when we think about, because it says we are saying evaluate this expression at all these real numbers, then add up the results. And so the thinking is weird because we're plugging in a continuum and we've got nowhere to put the plus signs. Fortunately, the fundamental theorem of calculus comes along to save the day. So once we get over the weird thinking part, we need to upgrade the what are we plugging in part. So in the case of a double integral, we just got to describe a region that has all the points we're plugging into the expression. And we have to be able to do it in rectangular and polar coordinates. Then when we're describing a solid, we have to describe the solid in such a way, which is just going to be a list of all the points that we're plugging into the expression. Fortunately for our heroes, we've been able to get away with what's x between, what's y between, and what's z between. So that's the strategy that we want to continue to use as we go through more shapes. All right. Let's take a look at this particular problem. We want to start off with the volume of a right circular cone with a base radius of a and a height of h. I got tired of using the capital R, so I just switched to a for the radius. And we're going to put the pointy bit at the origin because we are going to want to slap some coordinates on this shape pretty soon. I want to start with a single integral in the style of a solid of revolution. So I'm going to grab this triangle. I'm going to grab this triangular slice. I'm going to make the vertical axis the z-axis because that's what it's going to be in my rectangular and my cylindrical and spherical coordinates. Now the horizontal axis, I'm just going to use x because that's traditional, but it could also be y. Because we're going all the way around the circle, we can use x or y to represent our horizontal stuff. And also all the symmetry is really going to carry us through and allow us to get away with this. Note that we know what the volume of this cone is. It's 1/3 pi a squared times h. 1/3 pi a squared h. So finding the volume of the cone is not the point. Setting up the different integrals for the volume of this cone is the point. I want to start with a single integral as kind of a review because, hey, remember? At which point students are like, oh, I don't know, is there a quiz today on this? And I'm like, oh, no. Then you're like, oh, then yeah, we remember. And then before you leave today, it's like, oh, is there going to be a quiz on solids of revolution tomorrow? And I'll be like, oh, no. And then you'd be like, oh, okay, then this is fine. So I'm going to start off by slicing perpendicular to the axis of rotation. So I'm going to go to my region and I'm going to draw where the slice shows up. I'm going to think about this cone as a stack of cylinders. And since my slice is going to be perpendicular to the axis of rotation, that's my delta z. I'm going to make a better approximation by making my cylinders thinner, increase the resolution on my cone. So with this delta z, if I'm going to slice perpendicular to the axis of rotation, the volume of the slice is pi times r squared times the delta z. I've got to go into my picture and label where r is. R is the radius of my circular slice. And a radius is always measured from the axis of rotation. So there's R. I've got to figure out what R is in terms of the delta variable, in this case, delta Z. So I've got to figure out what R is in terms of X and Z. So I'm going to take my slice and I'm going to label where X is and where Z is. There's Z and there's X. So we can see that R is just equal to X. But that's not helpful. This is a delta Z problem. I need to translate X into a function of Z. So I'm going to look at this line that's making this triangle and say this is the line. Z equals, let's see, rise is H, run is A, H over A times X. That's not the one I want. I need to flip this around to solve for X. So this tells us that X is A over H times Z. So over here, I get that R is equal to X. R is equal to X. And X is equal to A over H times Z. So now I can write R in terms of Z, which is what we want because it's a delta Z problem. So my volume of the slice is pi times the radius R squared times my delta variable delta Z. I'm going to replace the radius with A over H times Z. And that's going to get squared times the delta Z. Then we just got to integrate this over all the Z values where we have a slice, and that would be from 0 to H. In this case, my discrete Z, delta Z becomes our continuous DZ. And now we can see all the things that are going to happen. We can see we're going to end up with a H cubed. It's going to cancel out with the H squared and leave an H on top. And the 1/3 is going to come from the integral of Z squared. So everything worked out exactly as we had predicted. That was the point. So pi A squared over H squared. The integral of Z squared with respect to Z is 1/3 Z cubed evaluated from 0 to H. H cubed and H squared leave behind just an H. So I have 1/3 pi A squared times H, just like we had planned. Finding the volume was not the point, but now we know that our setup was correct because it produced the expected result. Any questions? We're going for insight here, not the volume of the cone. We already had that. We're just trying to get some insight. We want to see what the setup is going to be. This pi r squared, that's what really told us that slicing parallel was going to lead directly to the result. We're going to be able to see where everything comes from. This is a similar thing that happens when we talk about rotating a sphere, finding the volume of a sphere through rotation as well. There's also a 1/3 factor. Is that 1/3 factor the same 1/3 factor? Is it that same? We're integrating a square, so we're getting a 1/3 something cubed. Let's come at this from another direction, not actually another direction. Let's slice in another direction. Let's try this slicing parallel to the axis of rotation to see if that tells us anything. So now my delta variable is going to be the thickness of our cylindrical shell. We're going to imagine this cone as a bunch of shells. Here's going to be a typical slice. So the volume of the slice is 2 pi times the radius times the height oh, not this h here. A little sloppy in my notation, I guess. Times the thickness of the cylindrical shell. Now I'm going to have to get the radius and the height in terms of the delta variable. This is h, the height at a particular point, not the h. That's the height of the shell. So I'm going to use a capital H. This is going to be variable. Radius is always measured from the axis of rotation to the slice. So here's where my radius is going to be. And my height is always perpendicular to the axis, to the radius in a shell problem. I need to write R and H in terms, both in terms of X. I might need to make a stop in Z. So I'm going to go to my slice and I'm going to label where X is and where Z is. Z is from the origin to the bottom of the slice, and X is going to be from the origin to the slice, horizontally. So from my diagram, I can see that my radius R is just going to equal X. That's convenient. That's the variable that I want. My capital R is equal to X. So I've got the R taken care of. Note that my H is the part above the Z. So H, capital H, is this top piece, which will be the whole distance minus the z. So my capital H is going to be my little h minus z. Now this is no good. I can't have z's running around my delta x integral. So I need to go up to my the line segment and write down how z and x are related. So this tells us that z is h over a times x. And so that's what's going to go in for the z down here. My capital H is now little h minus little h over a times x. Now I've got r and h, capital H, in terms of x. I'm ready to plug that into the slice and then integrate. So r is equal to x, and capital H is h minus h over a times x. Now we need to integrate over all the values of x at which we have a slice. So the total, I'm going to pull out my constants. I've got 2 pi. I'm going to factor out this h as well. And then we're going to have the integral of x minus x over a. Or sorry, x squared over a. My discrete delta x becomes a continuous dx, and the values of x that we care about are from 0 to a. Now we can stop and predict with our calculus skills what's going to happen. Are all the things that are supposed to happen going to happen? Notice I've got pi times h. I need to replace that 2 with a 1/3 a squared. Is a 1/3 a squared going to be what's coming out of here? Well, actually, we're going to have to divide by a 2 as well, because I don't want that 2. Let's find out. So it's going to give us a 1/2 x squared. And this one is going to give us a 1/3 x cubed. So it looks like stuff is going to work out. We're going to be able to divide out a 2 and a 3 to turn that 2 into a 1/3. Questions? Looks like it's all going to work out. Although it's not going to work out on this page, because I didn't give myself enough space, as usual. So I still have 2 pi h. Then the integral is going to be a 1/2 x squared minus 1/3a x cubed, evaluated from 0 to a. So at this point, we can see that we're going to have an a squared. Both of these terms will produce an a squared, so I'm going to be able to combine them. We're also going to have a denominator of 1/6, or a denominator of 6. The 2 will cancel out with the 6 and leave a 3 in the denominator. So it looks like it's going to work. Any questions? How's everybody okay? I looked at this and I said, you should write that underneath. I'm like, well, there's not really enough space to write underneath. Then write it above. You're going to need this space right here. I'm like, oh, don't worry, it'll be fine. It wasn't fine. Any questions? What I like about this is that we know what we're headed for, this 1/3 pi a squared times h. Which constant popped out first? The pi a squared or the h? We can see in both cases where the 1/3 came from. In both cases, that 1/3 came from integrating something squared. When we sliced perpendicular to the axis of rotation, I was able to factor out the pi a squared part, and it was the h's that had to go. The integration took care of those, the h's. When I sliced parallel to the axis of rotation, that is along a, it was h that fell out of the integral, and is a that showed up in the integration. Which is exactly what we expected. Here in our delta z, it's the a that fell out in the constants, and it was the h that showed up in the integral. Because the delta z integral was from 0 to h, z equals 0 to z equals h. In slicing parallel, it was delta x, and in delta x, the h fell out in the constants, and a showed up in the integration because we were integrating over x, and that's where the a shows up on the x. So this is surprising from no direction. Any questions? How's everybody okay? In case you're wondering why I made these points, Michael, didn't you make these points last semester in Calc 2 when we were doing solids of revolution? And it was yes and no. We did the problems, solids of revolution, to calculate our volume of a cone, but we didn't point these things out. Truths that we might not be necessarily ready to hear at the time. You know what I mean? Like all of algebra is just arithmetic done over again, only instead of base 10, we're in base x. And not all of algebra, most of algebra is just, hey, remember arithmetic? It's base x now. But when you're teaching arithmetic to little kids, they're not ready to hear that. So you don't. Think back to integration. We had like partial fraction decomposition. That's a technique that you learn in Calc 2. It is not a calculus technique. It's just an algebra thing. It's undoing adding fractions, breaking fractions apart. But you can't do that in your algebra class. You can't just take everything that would be tagged as #algebra and stick it in the algebra class because it causes open revolt. I had to put down a revolution once. I'm like, well, I just did adding fractions. I'm going to do unadding fractions and teach people how to break them apart. And then there was like open revolt in the classroom. It was just a room of 4th graders, so it was pretty easy to deal with. I'm just kidding. I've never taught 4th grade. People were not worried that Leach is like, that is like, oh my God, Leach put down a revolution in his class of 4th graders. Was he beating up 4th graders? That wasn't the worry. The worry is like, oh my God, someone let Leach teach 4th graders math. It's like, oh no, that's not how it works. I can't walk into rooms of 4th graders because I'll just start swearing like ridiculous amounts. I can kind of keep it in control here. I'm not even sure why. I think it's because I'm recording myself, but I don't really care about that. But I promise you, if someone like in this room, in this class was like a parent and they had a little 10-year-old, how old are you in fourth grade? I don't know, a little fourth grader that'd say, well, fourth grade is off today, so I'm just gonna have to bring the kid with me. I would be swearing and I wouldn't know why. So I'm like, well, why am I swearing so much? Oh, that's right. Little fucking kid over there. So it'd be a disaster if I walked into a room full of fourth graders. We've got a math teacher coming in to teach us some special math today. And I walk in, all right, you little fuckers. Dang it. I gotta get my shit together. Dang it. See, that's how it would work. When I'm annoyed with myself, I would say, dang it. But when it's something I'm saying to children, that's when the swear word would come out. Super useful as like a bouncer. Because I can't actually be the bouncer, but the bouncer would like check an ID. Is like, oh, this ID fake? I might go, oh, this fucker think that works? Nah. He's like, all right, Leach was swearing. You must be a child. Get out of here. Anyway, what are we talking about? All right, this is what you want to do next. Same solid, right circular cone, base radius of A and a height of H. I want a double integral. Actually, I want two double integrals in rectangular and polar coordinates. There are some things that I haven't told you. What's our function of two variables for a cone? That's a little bit tricky. Think about this. It's going to be V-shaped from the side. It's going to be V-shaped from the side. How do we make a V shape? That's one thing you want to think of. And then I want the easier version, a triple integral. But I want 3 triple integrals in rectangular, cylindrical, and because I'm a very bad person, spherical coordinates as well. Can anybody tell why I'm a very bad person for asking for spherical coordinates? You'll find out. You're like, oh, spherical coordinates, this is fine because it's round from that angle. What about from this angle? Not round. Spherical coordinates is going to be really limited, or actually just going to be complicated. Not really complicated, more like annoying. Because instead of measuring with an angle, this part is flat. And spherical coordinates like, oh, dude, I'm really shitty at doing flat things. And like, oh, well, we're going to have to force it. Ah, you know what I'm talking about? You will, when you get to spherical coordinates, triple integral, volume of a cone. That's going to do it for today. I'll see y'all on tomorrow. Everybody have a good day, and thanks for playing. It's 5 integrals for tomorrow. 5.